Hi there. Now this is question B of still the same. We're still solving question 1. Now this is a different question. We're told to solve this linear homogeneous system. It's a homogeneous system. Now to solve this, the first step you're going to do is, now you observe that this doesn't look like the one we did previously, and that's because it's not in matrix form. So the very first thing you want to do is you want to rewrite the whole system here in matrix form. So you're writing this whole system here in matrix form. So we have this side, which is x prime, equals, then the coefficients here we have 3, 2, 4, 3, 2, 4, and we have 2, then 0y plus 2z. That's 2, 0, 2. And the next thing is 4, 2, 4, 2, 3 times xyz. So our xyz, we said x equals xy, xyz. So this is going to be x. So we've written the whole system here in matrix form. Then the next thing is we want to identify the coefficient matrix. So we know that this is the coefficient matrix. So our A equals 3, 2, 4. We have 2, 0, 2. And then we have 4, 2, 4, 2, 3. So to solve this, the next step, so which I'm going to call step 3, if we are okay with writing 2, 3, is to find the eigenvalues of A. Now to find the eigenvalues of A, it amounts to solving, so we want to solve A minus lambda I as the determinant of this equals 0. Now this is called the characteristic equation of A. So we want to solve this equation here. So to solve this equation, that we have A minus lambda I, and that equals, so it's like you're deducting lambda from all the diagonal entries. So that's going to be 3 minus lambda. You have 2, you have 4, you have 2, negative lambda, you have 2, you have 4, 2, 3 minus lambda. So this is what we have. Now equals 0. Now by the time you find the determinant of this matrix, that is going to give us lambda cubed minus 6 lambda squared minus 15 lambda minus 8 equals 0. So we solve this cubic equation. Now when we solve the cubic equation, we're going to have lambda 1 equals 8, and then lambda 2 and lambda 3 equals negative 1. Now this calls for concern. Let me write it loudly here. Let me write the lambdas that we have. We have lambda 1 equals 8. We have lambda 2 and 3 to be equal to negative 1. Now our aim is to find the general solution of the homogeneous system. Now because we have, now this is distinct while this is repeated. Now we have distinct eigenvalue here, and then we have repeated eigenvalues here. That's 2 repeated eigenvalues here. Now because we have this, we have 2 forms that we can have for the general solution of the differential equation. Now the first case is this. The first thing you need to know is that since we're dealing with a three linear system, we expect the general solution to be of this form: x equals c1x1 plus c2x2 plus c3x3. So where x1, x2, and x3, they are actually fundamental solutions of the system itself. Now, to find x1 is just simply, that is, x1 is actually the solution that corresponds to lambda 1 equals 8, and that's going to be c1. I said c1, sorry. That's k1 e to the power lambda 1 t. And while x2, now to find x2 and x3, it depends on the kind of eigenvector we obtain for this case here. Now case 1 is, by the time you find the eigenvectors corresponding to lambda equals negative 1, so let me write it, on finding the eigenvectors that corresponds that corresponds to lambda equals -1 if we obtain two linearly independent eigenvectors. Two linearly independent eigenvectors, say x1. Sorry, I could just call that let's call that say k1 and k2. So say k1 and k2, that is, if k1 and k2 are two eigenvectors that correspond to lambda equals -1, then we're going to have our x2, which we want to find, to be, that's the k1 now. Maybe I should use, since I've used k1 here, so I could just call this k2 and k3. So we're going to find our k2 to be, so x is going to be e to the power lambda 2t, and then our x3 is going to be k3 e to the power lambda 2t, the same thing. But then, if on finding our eigenvectors, and then we only obtain just one linearly independent that's maybe we only obtain just one eigenvector that corresponds to the eigenvalue lambda equals -1. Now we're going to have, that's case 2. For that case, which I just mentioned now, we would still have our x2 to be k2 e to the power lambda 2t, but then our x3 is still going to be the k2 that we have here. Then we have t e to the power lambda 2t plus then k3, then we have 1 e to the power lambda 2t. So I decided to write this so that you observe a trend here. Anyway, let's go ahead and see the form of the eigenvector we are going to obtain. So let's start by doing the simple one, which is for lambda 1 equals 8. So that's going to be step 3. So to find the eigenvector that corresponds to lambda 1 equals 8, I'm going to solve a minus lambda I x equals 0. So solving that, so we are solving for lambda equals 8. So for lambda equals 8, a minus lambda I times x equals, so it's going to be -5, we have 2, we have 4, that's 2, -8, we have 2, we have 4, 2, -5 times x, y, z equals 0, 0, 0. So all we have done here is we're taking the case of lambda equals 8. So in place of all this lambda, I'm substituting it with 8 there. So that's what we have for that case. And then to solve this system here, I need to row reduce this coefficient matrix here. And then on row reducing the coefficient matrix, what I obtain is 1, 0, -1, 0, 1, -half, then you have 0, 0, 0. So this is what you have here. Then our x, y, z still stays there. X, y, y, z equals 0, 0, 0. This is what we have. And then when we write this thing in matrix, when we write this in equation format, what we obtain is 1 times x, that is x, 0 times y is 0, -1 times z, that is negative z, equals 0. Then the same thing here, multiply, we have y minus half z equals 0. And when you observe this, we have our free variable. The free variable is z, so we can set z to be, say, 1. Now if z is 1, we can find y. Y is going to be half z, so our y is going to be half, and our x is going to be z, which is going to be 1. So we have been able to find, so we have found k1. So our k1 is 1 half 1 half 1, and which we could also, or we could choose our k1 to be, but since we have a fraction here, so I could multiply all the entries here by 2. It will be 2, 1, 2. So I'm going to choose my k2 to be this. sorry, my key want to be this anyway. So let me now find the eigenvector that corresponds to the next eigenvalue, which is lambda 2 equals negative 1. So I want to find the eigenvector that corresponds to lambda 2 equals negative 1 in the GFE. So we go for lambda 2 equals negative 1. So to find the eigenvector, I need to solve a minus lambda ix equals 0. So a minus lambda ix equals 4, 2, 4. You have 2, 1, 2. You have 4, 2, 4. Then my x here is x, y, z equals 0, 0, 0. This is what I have. And to solve this, I need to row reduce this matrix here, and I obtain 1 half 1. You have 0, 0, 0. You have 0, 0, 0. This is what we obtained. Then we have x, y, z equals 0, 0, 0. And this is exactly what we obtained. And then the next thing is, we want to write this whole thing here in equation format. So we multiply 1 times x is x, half times y, that is plus half y, then plus z equals 0. This is what we obtain here. Now if you observe, this system here has 2 free variables. So we have two free variables. The free variables we have, they are z and y. So the free variables are y and z. So to find the first linearly independent solution, which I'm going to call A, so we'll set y equals 1 and z equals 0. So if y equals 1 and z equals 0, on substituting that into this equation here, we obtain x as our x to be, so that's going to be half times as negative half minus 0, that's going to be negative half. And then for the second, that's for the second solution, we're going to set we'll set our y to be 0 and our z to be 1. So we'll set y equals 0 and z equals 1, and then we obtain our x to be negative 1. So for this part here, we have our k2 equals x, which is negative half, y 0, or by the time you multiply all the entries here by 2, you have minus 2, 2, so this is minus 1, 2, 0, and then our k3 here is going to be negative 1, 0, negative 1, 0, 1. So now you observe that corresponding to this lambda equals negative 1, I have 2 eigenvectors that correspond to the eigenvalue. So because of that, that brings me to the next case. That's the first case. That's it satisfies the first case which I described earlier. That is case 1. On finding the eigenvectors, we obtain 2 linearly independent eigenvectors. So that implies that this and this are 2 linearly independent solutions of the homogeneous system that we were given. So therefore, the general solution of the system is going to be x equals c1 into 212 e to the power 8t. That is, this is the eigenvector that corresponds to lambda equals 8 that we obtained above, plus c2 into the power into, then this is the eigenvector, the first eigenvector here. We have negative 1, 2, 0 that corresponds to the eigenvalue lambda equals negative 1. So lambda equals negative 1, then plus c3 times the other eigenvector that corresponds to negative 1, et. Now this is the general solution of the linear homogeneous system.